if you remember last time, we had this, it was a corollary to the theorem that we proved, and it went something like this, right? So if you had an isomorphism between fields, and you had a polynomial f in k bracket x, right? Then there was actually an isomorphism. This isomorphism here induced an isomorphism between the splitting fields. This one's the splitting field here for f, and that one's the splitting field for f prime. All right, so an isomorphism of the base fields, the field of coefficients, induces an isomorphism of the corresponding splitting fields. And as an application of that, what we could do is we could take our isomorphism to actually be the inclusion mapping between not the inclusion mapping, the identity mapping from k to k. So where'd it go? So something like this. So suppose sigma and sigma prime are splitting fields for f over k, and so let's let I from k to k be the identity, which obviously is an isomorphism from k to k. So then, so we have that sigma prime, which equals, oh wait, how do I want to say that? I don't want to say equals, do I? Yeah, sorry, sigma prime is a splitting field for I of f, but I is the identity mapping, so that's just f over k. So now by corollary 2.8, what we have, so we have an isomorphism J from sigma to sigma prime. And so, and even more as, such that J restricted to K is equal to I, right? So it's an extension of the identity map, which means that it leaves all of the coefficients of the polynomial fixed. And if you've noticed, I keep slipping and I keep saying the splitting field when I say, oh, I mean a splitting field. But now, what do we have? We have splitting fields, potentially two different splitting fields for f over k, and in the end, they're isomorphic. And they're isomorphic by an isomorphism that fixes k. So we can say, in other words, any two splitting fields for f over k are isomorphic, and even more, you can write this down, they're isomorphic by an isomorphism that fixes k. So now it's okay. So now I can say, okay, we now can say the splitting field. And so at this point, there's really two options to coming up with a splitting field. So note that Now we have two, I don't know if options is the right word, but I'll just use options. So two options for a splitting field. For F over K. And it depends on sort of two different situations. So the first one, so this is option one. If we have an extension, so if we have an extension L over K, where alpha 1 up through alpha n in L are the roots of F, then we know that the splitting field, say sigma, equals K adjoin alpha 1 up through alpha n. Right? So in some situations, you are aware beforehand of a bigger field that contains all the roots. In that case, then you can do it by just adjoining those roots to K. But sometimes, right, you might not have immediate prior knowledge of this bigger field that holds all the roots, right? I mean, sometimes you know who you're working with, and sometimes you just know about K, and you don't really have this bigger place where that contains K and all the roots. In that case, then what you do is you just make use of a Kroneker's theorem. So the other one is to construct, and I'll use sigma prime via Kronecker. So what do? Right, Kronecker gives you a way to root by root of your polynomial, root by root, it allows you to find a place that contains the roots. So it allows you to build this L one root at a time. And what does our previous corollary or our previous observations show us? It shows us that in the end, algebraically, these are the same. So, so as sets, these are not necessarily equal. So as sets, sigma is not equal to sigma prime necessarily, or may not be. I'll just say not equal to. But they are isomorphic. So algebraically, it's all the same, which means that we can say the splitting field. And the second thing, and I actually want to say this, so let's say also note that the isomorphism in the case that we have K, so let's say it like this. So the isomorphism sigma, or sigma to sigma prime is, and this is sometimes referred to as an isomorphism of the extension. So is an isomorphism of the extensions. I got to be a little bit careful here. Sigma k, sigma prime over k, right? So if k lives inside both of these things, like we did in that previous example, then extensions, meaning that this would be j, right? Meaning that J fixes. Okay. Now, there's another consequence of that theorem 2.7, that hard one that we proved last time. So I want to look at that one now. So this is corollary 2.9. So let's let f in k bracket x be irreducible. Over k. And let's call sigma the splitting field. So and let sigma be the splitting field for f over k. Now, if we have a couple of roots of our polynomial, so let's say given alpha and beta in sigma, such that so maybe I should say if. I want to say if. Yeah, let me say if alpha, beta, I just don't like the way my sentence is going. If alpha and beta in sigma are such that f of alpha equals f of beta equals 0, then there exists an automorphism little sigma from capital sigma to capital sigma. And what does this do? Well, it fixes k and takes alpha. Oh, that's a ugly. That's not a v. That should be a beta. So this automorphism that fixes k and maps alpha to beta. In other words, sigma of alpha equals beta. Okay, so first, since f is irreducible, it's going to be a multiple of the minimal polynomial for alpha. Oh, and also minimal polynomial of beta. And since it's irreducible, it's going to be a scalar multiple, not a polynomial multiple. So since f is irreducible, f is a scalar multiple of m sub alpha and also m sub beta. Oh, and in fact, let's see, well, it's going to have to be the same polynomial, right? Because alpha and beta are both roots of f, so m sub alpha, which equals m sub beta. So what does that tell us then? It tells us that sigma is it's the splitting field for f, which means it's the splitting field for m sub alpha and m sub beta. So it follows that sigma is the splitting field for m sub alpha, which equals m sub beta. Now, so I'm going to set this up correctly now. So let's let I from k into k sub beta. Now what I want I to be is the inclusion mapping. So this, so let's be the inclusion right? So it just sends every little k into little k viewed inside k adjoint beta. So then I of m sub alpha of beta equals I of m sub beta of beta, which equals m sub equals m sub beta of beta, which equals 0. So now by theorem 2.5, right, there exists an extension J from k adjoint alpha to k adjoint beta of I, such that J of alpha equals beta. So now, two things to notice. So let's say observations. First one, J, so what's J of little k going to be? Well, that's going to be I of little k. I is the inclusion mapping, so that's just little k for all little k in capital K. And then the second of the observations, if we take Z in k join alpha, oh no, sorry, I wanted k join beta, then we can express Z as a linear combination of powers of beta. So then Z is equal to S0 plus, I think I used S's. Oh no, K's are good. K. Equals K0 plus K1 beta plus Kn minus 1 beta n minus 1 for some k i's in capital K. So then, I'm going to apply, I'm just saying what things look like in the codomain here, or I guess in the codomain here. So then, if I look at J of K0 plus K1 alpha plus dot 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 plus Kn minus 1 alpha to the n minus 1. Well, okay, so what's going to happen? You apply J to all of the k sub i's, which just gives you the k sub i's. And then J applied to each of the alphas gives us beta. And so this is going to equal K0 plus K1 beta plus dot 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 plus k sub n minus 1 beta to the n minus 1, right? And that's equal to Z. So what does that tell us then? It tells us that J is an isomorphism. So, right, so since we already know J is a monomorphism, so since J is a monomorphism, we conclude that J from K adjoin alpha to K adjoin beta is an isomorphism. Okay, so now I want to apply corollary 2.8. And so since sigma is, I'm going to just make sure all the it's actually applicable. So since sigma is the splitting field for m sub alpha, and over, let's say it's over k adjoin alpha, and also sigma is the splitting field for m sub beta over k adjoin beta. By corollary 2.8, there exists an isomorphism call it sigma from capital sigma to capital sigma, which of course an isomorphism from sigma to sigma, that's what we call an automorphism. Such that sigma restricted to k adjoin alpha is equal to j. So now what so now sigma of alpha, well, alpha lives in k adjoin alpha, so that means that this is equal to j of alpha, which we know is beta, and sigma of little k equals j of little k, which equals k for all little k in capital K. Okay, so that's the last of our extension results. So I'm going to stop here. I'm going to do a few examples next time of looking at splitting fields, and then we're going to move on to the next topic, the next chapter. But these extension theorems, I always find a bit difficult and it's almost mystifying. Like, why do we need these, right? Well, I want you. What we'll start to see. I mean, think what we just showed. We showed in this last corollary right here that there's an automorphism of sigma taking one root to another. Well, what does that mean then? Well, what it means is that we've got these automorphisms that permute the roots. And so and you want to think of an automorphism as a symmetry of the set. So somehow we're developing this notion of symmetry going on between the roots of the polynomial between the roots of some polynomial. Okay, so we will see you next time.